Hello, welcome to your lesson on graphing quadratic functions. When you graph quadratics, they graph in a shape called a parabola. Let's get started. Okay, quadratic functions usually take on this form, y equals ax squared plus bx plus c. This is called standard form. A, b, and c, the coefficients a, b, and c are known as the parameters. For example, here's a quadratic, and we can see the a, b, and c parameters take on the values -2, 3, and 5. Here's another quadratic function. Now a is 0.3, b is -7, and c is -11. As we change those parameters, the parabola, the shape of the graph, changes completely. All right, so our question in this lesson is, how do the different parameters change the parabola's shape? To begin, before looking at that, let's practice with parameters. So again, a, b, and c are called the parameters. In each of these three functions given to you here, what are the values of the a, b, and c parameters? Check your work here. In a and b, it's pretty clear. Here's a, b, c. There's our three values. Here, also pretty clear. There's no number in front of that, but it's not 0. There's a 1 there, 1x squared. So 1, -5, and 2. In the last one, hey, it's written backwards. The a is always the coefficient in front of x squared. So 3, -4, and 6. Okay, we've talked about parabolas already. We've looked at them as shapes that we can manipulate to create models for real life things. So let's go back to the basketball shot, because again, our question is, how do the different parameters, a, b, and c, change the parabola's shape? So let's go to this basketball shot and take a look. So here is our basketball shot. Here is our standard form parabola. I'm going to change the a value and watch as the graph changes. So what do you see happening? As a gets bigger, the parabola gets narrower. Great. As a gets smaller, the parabola gets wider. When a becomes negative, look at that. The parabola is now facing down. It's concave down. And it has a maximum vertex. So when I make a positive again, look, it's positive. Now the parabola is concave up, meaning that the vertex is now a minimum point. Important things to know. All right, but in this case, I need a concave down parabola for this basketball shot. So I'm going to make a negative. B value. B value has a very interesting effect. We can talk about that later, but for now, check out what it's doing. It looks like it's swinging the parabola side to side in a way. C value. Interesting. Oh, wow, look, parabola's going kind of up and down with that C value change. Great. Let me change the A a little bit more. It's hard to get it just right. Just like it's tough to get a basketball shot to go in the hoop, isn't it? All right, there we go. Not bad, not bad. But we're starting to see what the A, B, and C do. All right, that's our goal here in this lesson, to understand that. Okay, so there was the perfect shot. There's the parameters that give me that perfect shot right there. Again, one more time. When A is negative, the parabola will be facing downwards with a vertex that is a maximum. That's when A is negative. This 6, what do you think this 6 represents? Take a look here. Okay, next. Well, now that you're learning these skills, you can do very useful things like make parabolas that match the shape of a banana, something you've always wanted to do in your life. Actually, I'm pretty sure you woke up this morning thinking, what is the parabola that models the banana I ate for breakfast? So, very good. All right, now, you are on Desmos, or if you're not, get there now. Okay, now you're on Desmos. Okay, maybe you're not. Let's get to Desmos. Are you on Desmos? Okay, last time I'm checking. Are you on Desmos? Great. Now that you're on Desmos, your job is to graph these 6 parabolas. You will enter that equation, and then you will fill this table. So A has been done for you. In equation A, it has an A value of 1, a B value of 4, a C value of -5. And if you graph that one, you will notice it has that y-intercept of 0, -5. Let's check that. Okay, let's check that one to verify. It was x squared plus 4x minus 5. I think I have it ready. Here it is, x squared plus 4x minus 5. There's the parabola. Notice it has a y-intercept of 0, -5. Notice also the parabola opens up. Okay, your job now is to continue. Enter the parabola for B, and then fill the table. Put in the parabola for C in Desmos, fill the table. Let's check. I'm going to see how you're doing by asking you to tell me what goes in row E. Okay, check all your work there. Row E we have here. Anyway, there's all of them. By looking at this table, you should be able to make two key conclusions. So what are two key conclusions? Please type in your two conclusions right now. Okay, let's check what those two key conclusions should be. Number one, C, the C value is the y-intercept. That should have been really obvious from here. You can see these C values and you can see the y-intercepts. Very clearly, C tells you the y-intercept. And we can very clearly see that on our graph as well when we had the basketball shot. When I was changing C, the graph goes up and down, and we have our y-intercept right here, and that y-intercept changes as I move C up and down. See? All right. Next conclusion. If A is greater than 0, in other words, if the A value is positive, and we talked about that already, then the vertex is a maximum. And we see that on our basketball shot as well. Right now, A is negative, and this is a maximum. Wait a minute, this is wrong. Let me change. That's better. It's like it never happened. When A is positive, when A is greater than 0, the vertex is a minimum. Let's check. When A is positive, so I'm going to make A positive. Oh, look, I made A positive, and the vertex is a minimum point. All right, when A is less than 0, that means when A is negative, the vertex is a maximum. And we see that in the two examples given here. So let's take a look. Here's one parabola. A is positive, and we can see here it is, green, and the vertex is a minimum. Here, A is negative. That means parabola is concave down, therefore vertex is a maximum. Here is your C value of 1, there's your y-intercept. Here's a C value of -7, there's your y-intercept. Well, it's off the graph, but it's going to hit at -7. Two key conclusions, must know those. Okay, some key points on a parabola. We've been talking about all these points. We have the vertex, and here we have a parabola with a negative A value, therefore the vertex is a maximum. We have these two x-intercepts, they're important as well. Sometimes there's a y-intercept, very important. These points are important for interpreting real-world things that are applied. We can apply parabolas to help us look at real-world phenomena, right? So in this case, the dolphin vertex gives us the height of the dolphin's jump. Here, when we looked at the dolphin, we could say how far the dolphin jumped by looking at the distance between these two x-intercepts. Okay, so here's the problem we're going to end with. A rectangular mirror has a perimeter of 260. So this mirror would have a perimeter of 260. Let's say the length of the mirror is x, which we have here. Find the height of the mirror in terms of x. So we want to know this height, but we want whatever we write here beside there to be in terms of x. That means it must be an expression that has x in it. To begin, though, we can call it y. That might make it simpler. Now, can you make an equation to start for the whole perimeter? Well, we know the perimeter is 2 x's, this and this, plus 2 y's, this one, and that makes the whole perimeter. That is equal to 260. But our goal is to write this in terms of x. So try that now from this equation. Well, that just means solving for y. 2y equals 260 minus 2x. Then we can divide everything by 2, and we get this. We have just found out that y is 130 minus x. So we have written the height in terms of x. 130 minus x. So we can replace this y with 130 minus x. So now, step 2. Find an equation for the area. The area of the mirror in terms of x. So simply, the area can just be x times y, right? X times y. But it says, again, in terms of x. So why don't we use that we figured out in the first problem in this formula, so that we have an area formula that doesn't have y, it only has x's. So what will the area be? Well, if we substitute that value for y, we know y is 130 minus x. Put that in this area formula, and now we have a formula in terms of x. We can go further by multiplying here, and that becomes negative x squared when you multiply those, and 1 plus 130x. There's our area formula in terms of x. Next step, plot a graph. So on your calculator or Desmos, enter this area function and see what the graph looks like. You may have to change the window of your graph to see it all. Here's what you should be looking at on your calculator. There's the function x squared or negative x squared plus 130x. All right, that parabola represents the area. it represents the area of this mirror depending on the x value, right? So for example, when x is 30, the area is this value here. Or when x is 50 here, we go up, then the area is this. So at some point, the area is going up and the area reaches a maximum. Now, D, find the coordinates of the points where the graph Okay, so those are our two x-intercepts, and it asks, what do these two values of x represent? Okay, next. Well, obviously they represent when the area was 0, because this is area here. So the area is 0 if we have an x value of 0. That makes sense. If this has no length, there's no area. Or if this has a length of 130, it will also have no area. Why not? Well, if this was 130, then this would also be 130, and those make 260. And that's already the full perimeter. So that means y has no length. So that makes sense if y has no length, that there's no area. So interesting, no area there, but in between the area changes. Okay, find the line of symmetry. There was a formula we learned last time using the two x-intercepts to find the line of symmetry. That formula is this. We add the two x-intercepts and divide by 2, because the line of symmetry is like an average. We're looking from between the two x-intercepts, finding the average, and that will be our line of symmetry. So in this case, that is 65. So there's our line of symmetry. You can see the parabola has symmetry around that line. That line of symmetry will always pass through the vertex. So now we know that vertex. So what does this line of symmetry tell us in the context of the problem? All right, the line of symmetry tells us at what x value, in other words, what length of the rectangle or mirror, will give us the maximum area. Since the line of symmetry passes through the vertex, that is our maximum point, so we can find the maximum area at that x value. Great, you're learning more and more about quadratics. See you soon.